Let's try that again. Welcome everyone to the December 2024 meeting of the Astronomical Society of Edinburgh. You've got me in the chair this evening, and it's my pleasure to bring the curtain down on our events for 2024, which has obviously been our centenary year. Our main event this evening is Professor Martin Hendry's talk on listening to Einstein's universe. Before I hand over to Martin, I'll do a very short intro and talk about what's coming next year in 2025. So first of all, some news. 2024 was a big year for us in a number of ways. One was it was our centenary, and the other was that we started to see lots of data from our new remote observatory in Spain. And this example of M82 is typical of the kind of images that many of our members have been able to produce using the data that this new facility has captured. So it's been great to see that come on stream during the course of that special year. Something else to look forward to, if you've been sending your Christmas cards, then you're further ahead of the game than I am. But if not, here's a happy winter solstice card for tomorrow, of course. And another example of a fantastic image created by Mark, again, using the data from our ASIRO facility. So enough about 2024. What is happening in 2025? So the first thing to note is that our first monthly session, our hybrid session, isn't on January the 3rd. I think it was felt that that was maybe a bit too close to January the 1st, and there might be a few sore heads still. So the first hybrid meeting is on January the 10th, Friday, January the 10th. On the Wednesday before that, we'll have our first imaging and observing group session, and that's a remote session for members only. Our mid-month session in January is on real images of exoplanets, presented by Dr. Jason Wang, and that takes us through January. And then in February, we have a presentation from Dr. Stuart McKechnie on the European Extremely Large Telescope. Our imaging and observing group session mid-February, 12th of Feb, and then our mid-month online-only session presented by Dr. Daniela Bustamante, John Mowat, and the first Chilean Observatory. So following up our very successful centenary year with a flying start to 2025 and an action-packed couple of months, look forward to seeing everyone at some of those events. So without further ado, it's now my pleasure to hand over to Professor Martin Hendry to take us through his presentation on listening to Einstein's universe. Professor Hendry, over to you.
Great, thank you very much. So let's just share my slides. I think now you've stopped screen sharing. That should all just work, hopefully. Yeah, and I'm sharing sound. Good, excellent. So let me just maximize that screen and tell me if it's appearing as it should at your end. Grand. Does that look okay? You're seeing the title screen?
Yep, we've got your title slide down. Thank you.
Super. Right. So what I'm going to do is I will, just so that it's not covering too much of the window at my end, I'll reduce the Zoom boxes with everyone in. Happy in principle for people to ask questions as we go along, but just because I won't necessarily see if people are waving their hands or putting their virtual hand up, by all means, let me undertake to make sure that I leave plenty of time for questions at the end as well. So in other words, through my talk, I may not be able to see if people are trying to get my attention. So if so, just call out. But of course, I'll stop screen sharing at the end, and I'll be able to see everybody again, and then be very happy to do lots of Q&A. This is the new virtual world we're in. Of course, it's a pleasure to be able to join you in any form, but I'm sorry I wasn't able to be there in person. I know the original plan was I was going to come through to give a talk in February. We had a sort of family health issue. I'm glad we were able to reschedule. And indeed, it's a great honour to be part of your centenary year. I'm delighted to be your last talk of 24. It's been a big year for you. It's actually been a special bicentenary year for me because, although I've done a number of talks for you in the past, I think the most recent one I was still head of physics and astronomy at Glasgow. Since then, I've been, well, I suppose you would say, promoted to vice principal and clerk of senate. And that has meant that I've had a leading role in celebrating the 200th anniversary of the birth of William Thomson, Lord Kelvin. So if I accidentally just lapse into a talk about Kelvin, I'll try to stop myself because I've done dozens of them over the course of the year. It's been great to be able to play a major part in celebrating that bicentenary. But I'm very much going to be talking tonight about what has unfolded in the worlds of physics and in particular astrophysics after Kelvin's death in 1907, and beginning really with the work of Albert Einstein on general relativity just a few years later. So again, the university-wide role keeps me very busy. So that was why my schedule was a bit congested this year, but delighted that we were still able to arrange this before the end of 24. So I'm here very much more with my Professor of Gravitational Astrophysics and Cosmology hat on, rather than Clerk of Senate. And in that role, I'm going to be talking about work I do as part of the LIGO scientific collaboration on aspects of how we detect gravitational waves and what we have learned from them in the 9 or so years since the first detection was announced. And indeed, I'll try to make sure I leave a good amount of time to talk about what lies ahead as well, because as my title suggested, it's not just about the dawn of this new field, but also the exciting future that lies ahead of us. And quite a lot of that will focus on how we are using gravitational waves to address big questions in cosmology to do with the rate of expansion of the universe, and in the future we hope also perhaps to be able to say something about dark matter and dark energy by using gravitational wave observations. So all of that to come. Just by way of a little bit more scene setting, I mentioned LIGO already. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. And until a couple of years ago, I was one of the division heads of the LIGO scientific collaboration. So with a sort of leadership role in the global collaboration. And a map from a couple of years ago shows that it truly is global. There are LIGO groups in many countries across the world, even if the majority are in North America. We're also working with our partners in the Virgo and Cagra collaboration. So Virgo is a European detector based in Pisa in Italy. I'll say a bit more about that later. There's not a great deal to say about Cagra yet. It's a gravitational wave detector in the Kamiokande mine in Japan, but it has now formally joined the global network of detectors. It's just not yet at the same kind of sensitivity that the LIGO and Virgo detectors are, but nonetheless, in the future, it will have an important part to play in the global network as well. And the scientific collaboration that supports the operation of the observatories themselves is represented by groups all over the world, as I said, and you can see some of the logos in there, including, if you look hard enough, you'll find University of Glasgow in there somewhere. So I'm no longer LIGO division head. When I was appointed clerk of senate and vice principal, I had to really sort of look at my sort of bandwidth to maintain the same scientific leadership role within LIGO. But in a way, it's given me a little bit more time to contribute to some of the specific astrophysics analysis efforts. And that's really what I'm going to concentrate on in the course of at least the first 2/3 of my talk. How have we gone about detecting gravitational waves with LIGO, and what have we learned so far? Let me begin that by just emphasizing that gravitational waves are not electromagnetic waves. They are a whole new spectrum of radiation, a whole new way of probing the universe. Over the course of the last century, essentially during the century that your society has been in existence, our knowledge of the universe has relied primarily on electromagnetic waves. And indeed, around the beginning of the 20th century, we only really had visible light to go on. But over the course of the 20th century, the EM spectrum opened up both to long wavelengths in radio and microwaves and to short wavelengths in X-rays and gamma rays. And that's really been a tremendous way in which to enrich and deepen our understanding of a whole range of astrophysical phenomena. But gravitational waves are a prediction of Einstein's general relativity, his theory of gravity, and they give us a whole new spectrum, a whole different way of understanding some of the most exotic and energetic phenomena in the universe. So I've already mentioned Einstein. It is very much a talk about Einstein's theories. But rest assured, I'm not going to be going into too much mathematical detail. Really hardly any at all. I'm hoping that I can slip in the famous E equals mc squared equation, and you can see that on Einstein's statue here in Washington, where I'm sitting on Einstein's knee, a good kind of metaphor for my own career. So I'll come back and talk a bit more about how E equals mc squared is important in the work we do. But the other equations shown in Einstein's statues, let me just make passing reference to now, and then rest assured we're not going to get bogged down in equations for the rest of the talk. The first one is probably a bit hard to make out anyway, and the notation is rather more esoteric, and those are the field equations of Einstein's general relativity. So they involve a lot of complicated mathematics, but really the physical ideas behind Einstein's general relativity, I'm going to boil down into the following slide and spend just a few moments on that. But it's worth also just noting that the middle equation is about the so-called photoelectric effect, which is actually what Einstein did get the Nobel Prize for, not for his work on relativity. And that photoelectric effect, which, elements of which we learn about in high school physics, really underpins the physics behind how lasers work. And lasers do play a very important part in how we go about detecting gravitational waves. Hence the word L in LIGO is indeed laser interferometer gravitational wave observatory, the inner workings of which we'll look at in a few slides' time. So Einstein's general relativity, if we take all the complicated maths out, then I think a good metaphor for what's going on, at least it's always worked for me. It's not perfect, but it does give us a sense of what the maths is saying, is that gravity is essentially the curvature of space and time. And in fact, gravity and acceleration are both equivalent to each other in Einstein's theory, and both manifest themselves as a change in the curvature of space and time themselves. And there's a very neat phrase attributed to John Wheeler, the American physicist that many of you I'm sure will have heard before, which I think captures the essence of Einstein's idea. It's that space-time tells matter how to move. The curvature of space-time determines how matter will move, so that, for example, the moon will orbit the Earth, not so much because it's experiencing a gravitational force, like Newton would have said, but instead the moon is experiencing the curvature of space-time in the vicinity of the Earth that's caused by the Earth's mass. And that's the second part of John Wheeler's phrase, matter tells space-time how to curve. So the curvature that's represented in cartoon form here is, like the stretched sheet of a trampoline onto which we've somehow dropped the Earth. It would have to be a very big trampoline, of course, but that curving of the surface of the trampoline is just a two-dimensional scaled down cartoon representation of the curvature of the four dimensions of space-time that general relativity associates with the phenomenon of gravity. And that means that the moon will orbit the Earth, not so much because it's experiencing a Newtonian gravitational force, but instead we can think of it as following the natural curved contours of the space-time in the Earth's vicinity. So that's our basic idea of gravity and general relativity. And where gravitational waves come in is when the gravitational field, the space-time curvature, is changing. So in that sense, in the spirit of the same kind of analogy we just saw in the previous slide, we can think of these waves as analogous to the electromagnetic waves that occur when the electric and magnetic fields change in, say, an atom or an antenna of a radio transmitter, for that matter. But the thing is, gravity is a lot weaker than electromagnetic interactions. So while we can produce measurable electromagnetic waves just by making electrons whiz up and down an aerial, and that's how we get radio. If we want to produce measurable gravitational waves, we need a much greater disturbance of space-time to produce an effect that we could hope to measure. So, for example, me shaking my fist is technically changing the gravitational field of my hand. But we could never hope to measure those gravitational waves. Gravity is just too weak. If you do look at the equations, the way that this comes out is in terms of what we call the coupling constant between the left-hand side and the right-hand side of the equations in, Einstein's statue. Or another way to think of it is that basically you need to change the curvature. Well, you need a lot of mass changing its gravitational field very rapidly to produce a change in the space-time curvature that we could ever hope to measure. So the animation here, again, just kind of a cartoon one, but is alluding to two stars which are very compact, very dense, stars like neutron stars, for example, which are orbiting very close to each other. So that means that the gravitational field is changing a great deal, and it's doing so at a very high velocity. You need velocities close to the speed of light, and you need masses close to the mass of a star like the sun, but compressed into the density of maybe just a few kilometers or a few thousand kilometers across, like a white dwarf or a neutron star, or indeed a black hole. Those are the kinds of changes in the gravitational field that would produce gravitational waves that we could hope to measure. And we, in this case, is the LIGO and Virgo and ultimately CAGRA detectors. But they have to be incredibly sensitive because these waves are weak to begin with, and as they spread out through the universe, the disturbance in our patch of space-time is even weaker. So to put some numbers onto that, if we take, let's say, two black holes, as I'm going to talk about in a few minutes, colliding together far away in the universe, a few 100 million light years or further, then by the time the gravitational waves that that event produces reach us, they'll disturb our patch of space-time by less than a millionth the width of a hair on your head, or about 1,000th the size of a proton in the nucleus of an atom. So we want to detect these tiny, tiny changes. How on earth are we going to do that? Well, that's where laser interferometers come in. LIGO, these instruments, laser interferometer gravitational wave observatories, are the most sensitive scientific instruments ever built. And they are capable of detecting the tiny changes in the curvature of space-time that I've just been referring to, produced by things like the collision of two black holes or neutron stars far away in the universe. So the two LIGO detectors are located in Livingston, Louisiana in the top right, and Hanford, Washington in the bottom left. They were conceived in the 1980s, and construction sort of unfolded over many years, of culminating in them being operated but in a less sensitive configuration in the early 2000s. But in 2010, upgrade work began to make them more sensitive, to convert LIGO into advanced LIGO, as we called it. And I'll say a bit in the coming slides as to what changes were made to make the detectors more sensitive. So before I get to that, though, let's just unpack a little bit the basics of how interferometry actually works in this context. And again, I've made the animations simple, I hope, but nonetheless instructive also, I hope, because they do capture the essence of what's going on. So what we basically have is two arms of an L-shaped interferometer along which laser beams of light are directed, first having been split at the beam splitter, and then those lasers are bounced off mirrors at the end of the arms, and then when the light returns to the beam splitter, the laser beams are recombined. And if a gravitational wave has passed by, what it will do is change the path length travelled by the two laser beams. What you get is a stretching and squeezing of space-time, a bit like the cartoon on the right. And that results in a change in the phase of the laser light that goes along one of the arms compared with the light going along the other. And that change in phase shows up as a change in the interference pattern, hence the interferometry in the name, and between the two laser beams. So that's what's sort of being represented in cartoon form in the animation on the left. What we're seeing is that the stretching and squeezing is changing the effective path that the beam is traveling, and then that's changing the interference pattern in the right-hand part of the animation. Now, this is greatly simplified compared with the reality of all the kind of optical components inside LIGO. And in particular, the effective path that is traveled is thousands of kilometers because the laser light is kind of recirculated within the arms of LIGO hundreds of times. What we get is an optical cavity, which makes it more sensitive than if it was just traveling once back and forth along the arms. So it's a sort of resonant cavity that builds up greater sensitivity and builds up a greater path difference ultimately between the two beams. Now, the instruments are still big. The arms are 4 kilometers long, but this signal recycling that is done turns them into a much, much longer effective path length. And it's that that ultimately gives LIGO the sensitivity required to detect these tiny changes caused by a passing gravitational wave. But crucial is to understand the type of signal that we're looking for. So hopefully what you're seeing is a small animation in the bottom left, which is just representing, again, just a kind of simple cartoon of two black holes spiraling in towards each other, and they eventually coalesce after a few seconds. Now, while they're doing that, they're sending gravitational waves out into the universe. Of course, they actually would go out in 3 dimensions, but we're just showing it in 2 for simplicity here. And as the black holes get closer together, then the frequency of the gravitational waves becomes greater and the amplitude of the gravitational waves becomes greater. The black holes are disturbing space-time more violently and more rapidly as they get closer together. So that produces a distortion pattern, which is shown in the graph. So what we see is a kind of sine wave-like pattern, but the peaks and troughs get closer together, and also they get more stretched out in the vertical. So increasing frequency and also increasing amplitude. And then at the point where the two black holes are merging, that's pretty much where you get the peak amplitude. And after that, you've just got one black hole, which still wobbles a little bit more as space-time settles down again, so the pattern fades away. So we call this altogether a chirp, and it's got 3 components: an in-spiral phase, as the frequency and amplitude is increasing, a merger phase, where it reaches the maximum amplitude just as the black holes are merging, and then things sort of damp out as the single remnant black hole sort of wobbles some more. We call that the ring down phase. So these 3 phases were studied both analytically and then ultimately via very detailed numerical computations through the 1970s and 80s and 90s. And in the mid-2000s, some really important breakthroughs were made that allowed us to model numerically the whole waveform through the in-spiral, merger, and ring down phase. So what this meant was that we kind of knew what we were looking for. Or to echo the title of my talk, you might say we knew what we were listening for, because the frequencies that correspond to the frequencies that LIGO can detect are actually frequencies that the human ear can hear. Gravitational waves are not sound waves, but we can render them as sound waves, or at least think of them as sound waves, as a way of interpreting the data differently from just a graph. We can interpret the data as a sound, and that sound we call a chirp, and it's a very characteristic pattern where the frequency increases and then fades away. So that's really what you're seeing in the graph, and we'll look at some more chirps and possibly hear them. I can't remember if I included a slide, but perhaps many of you will have heard that before, because it was widely publicized at the time of our first detection, the sound of space-time ripples. But let me emphasize, gravitational waves are not actually sound waves, but it was a very useful way for us to convey some meaning as to what we were seeking to detect. And I think just to extend that metaphor a little further, if we do think of gravitational waves as sound waves, well, the problem we principally had was a lot of background noise. It was a bit like being in a busy lunchroom at a high school and trying to pick out a conversation, even in the person opposite you on the table. If there's so much background noise, it's very hard to make out what that person is saying. But if you know what they roughly are talking about, you know, what they might be talking about. In other words, having a good model for what their conversation should be about, then it's a little bit easier to pick out what they're saying, even with a noisy background. And that, I think, is quite a good analogy too for the way that we went about our data analysis in LIGO, armed with these good models, theoretically, for what the gravitational wave distortion ought to look like or sound like, as we were seeing in the previous slide, the model predicted waveform showing the in spiral, the merger, and the ring down. So this, again, not the most straightforward of graphs, but I think I owe it to you to give you a bit more of the background detail here. So again, let me try and walk you through what's going on here. This is a way of describing the sensitivity of the detector as a function of frequency. So one way we can measure that is in what we call the strain noise, which is essentially a measure of what distortions in space-time we would be capable of measuring. It's a dimensionless number. It's to do with like the fractional change in the arm lengths of the detector. That's how we actually kind of how it manifests itself, how we measure it. But what it's telling us about is changes in the curvature of space-time itself. And again, we're looking at, 1 part in 10 to the 22 or 10 to the 23, an absurdly small number. But these are numbers that we were on the brink of being able to detect around the turn of the 2010s. With what's called the S6 run. That was the last run of initial LIGO. And then in 2010, LIGO underwent upgrades to turn it into advanced LIGO, and that got us more sensitive, which means that the sensitivity curve was lower. Now, there were lots of individual frequencies where the sensitivity was much worse. So those are showing up here as the green and red spikes. But outside of those narrow frequency bands, we had much better sensitivity. And they're almost a bit analogous to the fact that, there are certain wavelengths of light or frequencies of light where the sky is very bright because you've got sodium from old-fashioned streetlights and that kind of thing. So we've got the equivalent of that in the gravitational wave spectrum as well. There are certain frequencies where the terrestrial interference is so great that we can't really hope to measure anything. But what we can do is design the detectors in a way that can confine those sources of noise to narrow frequency ranges, and outside of that, we've got better sensitivity. The overall shape, nonetheless, is less sensitivity at very low frequencies, a few tens of hertz, and also at very high frequencies. But we've got this region in the middle, a kind of sweet spot, where we can make better use of the detector technology and achieve better sensitivity. And there were three main aspects that turned initial LIGO into advanced LIGO. One was better isolation from the vibration of the detector and ultimately the Earth at low frequencies. Another was the use of higher power lasers, which improved the sensitivity at higher frequencies. So that's essentially how we got from the green curve to the red curve at either end. And then in the middle, it was about using mirrors which introduced less thermal noise. The mirrors didn't shake so much, partly because of the way they were suspended. I'll say something about that in a moment, but also because the mirror coatings were designed to introduce less noise due to just thermal disturbance in the mirrors themselves. In terms of how the mirrors were suspended, the big change was to go from having steel wires in initial LIGO to silica fibers in advanced LIGO. And our Glasgow group led that work. So I wasn't involved in that because I stick to the theory and data analysis, but a number of my colleagues in the experimental side of the group made, really huge breakthroughs there, which were adopted by the LIGO project and my colleagues played a major part, along with many others within the UK, in improving the sensitivity of the LIGO detectors to get us to the brink of the first detections. So it really was a good news story for the UK in terms of making a contribution that was a real game changer for how LIGO worked, even though in terms of the overall cost of the project it was relatively cheap, but it was a good investment on the part of UK Research and Innovation, as it's called now, through the Science and Technology Facilities Council, or STFC. And as promised, here is the sound of that first detection. So I'll stop talking so you can hear it properly. Let me just freeze it there. So I'm playing it over and over again, which of course the real signal didn't work like that. It just lasted for a fraction of a second and then it was gone. But this is the signal that we detected on September 14th, 2015. It was a signal, as I'll explain in more detail in a moment, that we were able to deduce came from the collision of two black holes more than 1 billion light years away. And what you're seeing, and indeed were hearing, was the pattern detected by LIGO Hanford and LIGO Livingston. These are 3,000 kilometers apart. So hopefully what strikes you as quite noteworthy to begin with is how similar the two patterns are, shown in orange and blue. And then what you're hearing is, well, the kind of low rumble, which is the background noise of the detector, turned into a sound pattern. And then over and above that, you can hear, well, frankly, in the original frequencies, it sounds a bit like a dull thud as those two black holes collide. But then what I've done is I've shifted it to higher frequencies, a bit like what we do with false color optical images to bring out the detail rather better. And I think the human ear can hear the chirpy-like pattern rather better at those higher frequencies. So let me play it again and see if you can sort of pick all that out. So again, many of you may have seen or heard this before. I know it's been widely publicised since that first detection, but I thought it was worth just talking through what's going on so we can see the in-spiral, the merger and the ring down, which was nice and clean in the theoretically predicted waveform. It's a bit noisier, of course, but it's still quite distinctive in both Hanford and Livingston. So when these data came through on September 14th, 2015, really, we were pretty confident from the get-go that we had detected something. But what began then was a very intensive period of about 5 months of very, very careful analysis to make absolutely sure before we announced a detection that we hadn't messed up. So we wanted to first verify that it really was a gravitational wave detection, but we also wanted to characterize the properties of the source that had produced it. We wanted to work out if these were black holes, then how massive were they, how far away were they, that kind of thing. So what unfolded over those 5 months, as I say, was lots and lots of hard work, lots and lots of analysis, which ultimately led to the announcement of that first discovery on February the 11th, 2016. So here is our news page from that day, and actually just from a few weeks later. But what we had announced, was very quickly picked up by the world's media. We were on more than 900 newspaper front pages the following day, so this was a big deal. And still looking back, it was quite an amazing experience to be part of all that, to be shaping how we told the story of that first ever detection to the world's media. So what exactly had we detected? So here's those two waveforms in a slightly different way of representing them. Now superposed, you can see how similar they are. And again, the three phases that we referred to before, the in-spiral, the merger, and the ring down, are shown in correspondence to the data themselves. So what we did was to analyze those data using the methodology that we developed over many years before to extract from the waveform information, estimates of the parameters of the source. So things like, as I said, the masses of the black holes and the distance to the source. And what I've got now is a little animation which just explains again in cartoon form, roughly how we did that. So of course it involved lots of computing and lots of, hours and hours of analysis. But my colleague Laura Nuttall from the Institute of Cosmology and Gravitation in Portsmouth is just going to, for a few seconds, talk through more or less what's going on and think of it in terms of template matching. So what we've got is a set of theoretical templates showing the gravitational waveforms that different masses and distances would produce, and we were trying to match those to the data, and that's what Laura will briefly describe.
On the 14th of September 2015, one of these tiny gravitational wave signals was detected by LIGO. By comparing the signal to the predicted signal, scientists are able to find out more about the origin of the gravitational waves. To determine the mass of the black holes and their distance, we can compare with theoretical models. The parameters of the model are adjusted until the predicted signal matches up to the data. The closer the black holes, the larger the amplitude of the detected signal. The mass of the black holes can be changed. The lower the mass, the higher the frequency.
Okay, so what we deduced was that this was an event that had basically happened a long time ago in a galaxy far, far away. The two black holes were at a distance of more than 1.3 billion light years, and more than 400 megaparsecs, and their masses were about 30 times the mass of the Sun. More precisely, one of the black holes had a mass of 36 times the mass of the Sun, and the other had a mass of 29 times the mass of the Sun. And over the course of just a fraction of a second, during the final part of their in-spiral, those two black holes had merged and released a burst of gravitational wave energy, which the LIGO detectors had detected. And by doing the analysis roughly in the manner that Laura described, we were able to estimate the mass of the black hole that was left behind. And that was of a mass 62 times the mass of the Sun, which is not the same as 29 plus 36. So in the course of just a fraction of a second, the equivalent of about 3 times the mass of the Sun was converted into gravitational wave energy. So this is where, as promised, I'll return to E equals mc squared, because if that's how much mass was converted into gravitational waves, then we can use E equals mc squared to tell us how much energy that was. And if that energy was released in just a fraction of a second, say, let's say about a third of a second, we can estimate how much power in gravitational waves that corresponds to. Or if you like, what luminosity in gravitational waves that corresponds to, because that's really what we mean by luminosity in relation to a star or a galaxy. It's the light power that the star or galaxy is giving off. Well, this is the gravitational wave power that's been given off. And that corresponded to about 50 times the light power of every star in every galaxy in the entire universe. So it gives a really mind-blowing insight into how much energy is locked up in the fabric of space-time, waiting to be released in these extreme events like black hole collisions. And the remarkable thing for me was that all of this was happening without any light being given off at all. Or at least we don't think there was. We don't expect there to be any light from a black hole collision. So collisions like this would have been happening regularly throughout the universe long before the LIGO instruments were even conceived, never mind built. It's just that now, for the very first time, we could listen to the consequences of those events. And all of that was giving us this insight into the dark side of the universe, if you like, which we'd never had before. And as a big Star Wars fan, that reminded me very much of the immortal words of Darth Vader when he said you should never underestimate the power of the dark side. So that little calculation we've just done, very crude, but you get a real sense of how much gravitational wave power is locked up in the dark side of the universe, in the fabric of space-time, with no electromagnetic radiation associated. So this was a big deal. It was awarded the 2017 Nobel Prize in Physics to 3 of my senior LIGO colleagues. That was a great honour. But in fact, when that was announced in October 2017, we were actually very busy because, of course, it didn't stop there with that first detection. There's been lots more detections since. So let me move on to describing all of that. So the next big landmark was in August 2017 when a third detector began operating. That was Advanced Virgo. So again, upgraded in a similar way to LIGO with more sensitive laser interferometers. And what that meant was that we could, in principle, determine the sky position of sources more precisely. Because with only 2 detectors, what you can do is use the arrival time of the gravitational waves to give you information about where on the sky they came from. Gravitational wave interferometers are a bit like radio telescopes in the sense that they're not, just seeing a very small part of the sky like an optical telescope. They're sensitive with an antenna pattern, not that different from a radio telescope, to a large part of the sky in one go. But the different arrival time would correspond to a ring of positions on the sky, each of which would have the same arrival time difference for any 2 detectors. So if you've only got 2 detectors, then essentially you can't really say where the source was other than it's somewhere on that ring on the sky. But with 3 detectors, you get 3 pairs, 3 rings, and where the rings intersect, well, that's where you've pinpointed your source to be. So within just a couple of weeks, we had a source, another black hole binary collision, which was localized to about a factor of 10 better than the previous detections had been, including the very first one that we were just discussing, 150914, 14th of September 2015. But this one on the 14th of August 2017 was localized to only about 60 square degrees because Virgo was now giving that extra information to pinpoint the position. And just 3 days later, Virgo again proved its worth, proved its usefulness, because we saw an event that was observed in gravity and in light. It was a merger of neutron stars that was observed by NASA's Fermi satellite, the ESA integral satellite, and most importantly by LIGO and Virgo. So what we saw, let me just again represent it both visually but also in sound. So that burst of gravitational waves corresponding to the upward sweep of the chirp was followed by the ping corresponding to the arrival of gamma rays less than 2 seconds later. Now we believe that that's because the gamma rays set off about 1.7 seconds later. In other words, the gravitational waves and gamma rays are really traveling at exactly the same speed, the speed of light, exactly as Einstein's theory predicted. And frankly, even if they did set off and got out of step along the way, this was a source about 130 million light years away. So to only lag behind by 1.7 seconds over 130 million years tells us that the speed of gravity and the speed of light must be almost exactly equal. Einstein theory predicts that they're exactly equal. Now we've got experimental verification of that. And the sky position, as I said, was more precisely determined than would have been possible with just LIGO on its own. And that pinpointed this event associated with the gamma ray burst to a galaxy, NGC 4993, in which what was observed in optical and infrared telescopes, the aftermath of a neutron star collision, what we call a kilonova. So here it is, here's the before and after photo with HST and then a ground-based telescope SWOPE that picked up this remnant event indicated by the red arrow. So there's a lot I could say about this event. There isn't really time to go into the full details because I want to, update you on what's been happening since 2017. But this is, one of the most studied astronomical events in history. And from our perspective on the gravitational wave side, it's been extremely interesting because it's given us a way to measure the expansion rate of the universe using gravitational waves. We still need the optical observations to get a redshift, but we get the distance from gravitational waves. And again, I'll return to that in a few minutes as I kind of round out my talk with some of the latest discoveries. Jumping ahead to 2018, we published our first catalogue of events then, which at that point had 11. So that was 10 binary black hole mergers and this binary neutron star merger that we've just discussed. And then we underwent further upgrade work and began our third observing run on April 1st, 2019, so just about 5.5 years ago. And that third observing run ran for well, it ran for more or less a year. And during that time, we were putting out public alerts about candidate gravitational wave events. That was a change from the earlier observing runs. So some of you might even have been following those on your phone. Our colleagues at Birmingham University put this app together. It's a very nice piece of software. And over the course of that observing run, O3, which ended just a bit early because of the pandemic in March 2020, the number of events we observed jumped to a total of 90. So that was 79 new events in the first and second half of O3. So that took us through to 2020. So we published in 2021 a catalogue of our all of our events to date, which comprised that 90 event total. But let me just highlight a couple of examples of them. So here's one from the 12th of April 2019. This was a binary black hole merger, but this one had a very much smaller in mass black hole orbiting a more massive black hole. And that gives us a much richer pattern of gravitational wave signal. It's a bit like a musical note. When you play it as part of a chord, it's got harmonic structure in addition to just the main frequency of the individual note. So we got that in this event, and we publicised that as part of the story of how this event was a bit special because it was unequal masses. And then, in fact, just a week or two after that, we got another binary neutron star detection, which again we were able to analyse carefully, but this was much more distant and it wasn't accompanied by an electromagnetic counterpart, either a gamma ray burst or a kilonova, or at least not that we observed. There might have been one, but we didn't detect it. And to give you a sense of that, well, the data is shown here as a time frequency plot, and in fact the chirp pattern is there. It's just kind of blinking in and out. Maybe I need to sort of help guide your eye a bit more. There it is. In fact, I haven't quite lined up my dashed curve quite correctly, but the point is that's much harder to spot by eye than the event that we observed in 2017 that was much, much closer and much louder in gravitational waves. But nonetheless, our search algorithms can find, digging out from the noise, these fainter signals, and that's what we did here. And in fact, we found that the two masses of the neutron stars were quite a bit more massive than the types of neutron stars that we typically see in our own galaxy. So it's giving us a hint that there's a broader global cosmic population of neutron stars beyond those that we detect with radio. For example, the one that Jocelyn Bell famously detected. Those are just part of the story. Another one that we detected also in that observing run was an example of a much more massive black hole merger, where the two stars, the two black holes that produced the merged black hole, were already themselves dozens of times the mass of the sun, and the merged black hole was well over 100 times the mass of the sun. So this gives a very short waveform, but it's an example of what astronomers refer to as an intermediate mass black hole. And because those two initial black holes that merged were already themselves pretty massive, it makes it quite possible that they too were the result of an earlier black hole collision. So you have a kind of hierarchical building up of more and more massive black holes. And well, that's quite a plausible idea, because we do know that many galaxies, some astronomers would say most galaxies, have a supermassive black hole at the centre with masses more like millions of times the mass of the sun. So one way to build those up would be out of less massive black holes like this one that we saw in May 2019. The final event I just want to highlight from this part of our third observing run was in the 14th of August 2019. This was another pair where there was a big inequality, unevenness between the mass of the bigger black hole and the mass of the smaller object. In fact, the smaller object could have been a neutron star. We think it was more likely to have been a black hole, but it wasn't clear. And that ratio of masses of about 9:1 again gave this rich pattern of harmonics in the gravitational waveform. Just let me play that again, which can give additional information and constraints on how massive the black holes are. So basically what was emerging was this really rich pattern of events, the vast majority being black hole mergers, but a couple of neutron star mergers as well. And then in early 2020, just before the run ended, we got two examples of events where you had one black hole and one neutron star. Now, of course, this isn't a photograph, it's just an artist's impression, and it's frankly a rather fanciful one, but it certainly grabbed the media's attention because, of course, this was a different sort of event, and what we had was, well, some data about not one, but actually two mergers of a neutron star and a black hole. And we were able to look at simulations of events like that, which I'll just show these animations. Let me get them both started. And what the two animations are showing is quite different end states. So in the upper one, what we've now got in the insert is the black hole and the neutron star orbiting each other. And what we're going to see in a moment is the neutron star being swallowed almost in one gulp by the black hole, quite dramatically. Whereas in the lower animation, maybe I'll run that one again, what we're seeing is that the neutron star is being stripped apart much more slowly. Okay, it's still all unfolding pretty fast, but you can see that the tidal disruption of the neutron star is causing it to really sort of spill its guts around the black hole. So these are both scenarios that could happen. And if it was the lower, then we would expect there to be accompanying electromagnetic radiation. We would also see some subtle differences in the gravitational waveform due to the tidal distortion of the neutron star. We didn't see that in the case of our two events in 2020, so that rather points to these being the neutron star swallowed whole by the black hole, a bit like the upper animation. Or as I've liked to put it in schools talks, it's a bit like comparing Pac-Man and Cookie Monster. Pac-Man sort of swallows his energy tablets in one gulp, whereas Cookie Monster is a notoriously messy eater. So some black holes could indeed be notoriously messy eaters when they swallow a neutron star, but it doesn't look as if the two events we saw in 2020 were like that. If we were to see such an event, it would give us an opportunity to probe the internal structure of a neutron star and understand a bit more about the equation of state of the matter, which is in incredibly high densities and pressures, but to understand exactly what's going on inside such a neutron star. So that's another area that we would hope to explore further in the future. So here's our O3 catalogue with the 90 events. So we actually published that more than 3 years ago. So I want to make sure that I get you fully up to date because our fourth observing run has been underway since, in the interest of time, let me just skip over that one. You can always ask me about it later. Oh, forgive me, I forgot I had a little bit to put in here. I don't want to skip over this because I hope I'm not overrunning too much. But another 10 minutes or so, is that okay? Yeah, sorry. It's difficult to cover all the historical stuff quickly because there's so much to cover. So anyway, let me press on. So we're still talking about our third observing run. This is just to remind you of that animation I showed from Laura Nuttall, where she was emphasizing that we could also estimate the distance of gravitational wave sources by essentially pattern matching the waveforms. So if we can do that and we can get redshifts, then we can estimate the Hubble constant, the expansion rate of the universe. Now, getting the redshift for the neutron star merger that was observed in 2017 was relatively easy because we knew which galaxy it was in because we saw an electromagnetic counterpart. But with only one event, we couldn't estimate the Hubble constant very well. So what this blue curve is showing is our estimate of the Hubble constant. The numbers are there as well if you want to look at them. But really, in terms of the graph, what it's showing is that we're getting a Hubble constant in the right ballpark, round about 70, but not with sufficient precision to say anything about what people are referring to as the Hubble tension, the disagreement between different methods of estimating the Hubble constant from either nearby or far away sources and methods. So we've got the far away methods based on kind of extrapolating backwards from the cosmic background radiation. They're consistently giving values about 65 or 68, whereas the nearby methods like Cepheids and supernovae are giving values more like 73. So we're very much in the right ballpark, but really from a single observation, we were never going to be able to resolve the Hubble tension. So what's happened since then is that we've expanded our sort of catalogue of sources to the 90 that we saw before. Most of those, of course, are black hole binaries. We don't get an electromagnetic counterpart from them. So what we had to do was to devise a different way of getting the redshift. We don't know the true host galaxy, so what we have to do is look at how well we localize the event on the sky and in distance, and then identify potential host galaxies and average over them, or the technical term is marginalize over them. So this is quite heavy-duty statistics to try and do. From a single source, you're not going to get the Hubble constant very well, but the hope is with enough, then you'll home in on the correct value. So that's been a big piece of work that we've led at Glasgow, mainly through the work of our former student Rachel Gray, who's now back as an academic staff member. And it's been, really interesting to be involved in all of this. So bottom line, what we've been able to do is to improve slightly our estimate of the Hubble constant. So let me walk you through this. So the orange curve is the one that we were looking at before, where from the single binary neutron star merger in 2017, we didn't get a very precise measurement of the Hubble constant. If we include some of the black hole binaries doing this trick of averaging over all the possible host galaxy redshifts, then it sharpens up a little bit. But the result is still kind of dominated by the binary neutron star, where we knew for sure which galaxy it was in, so could get a more reliable redshift. So this was back in 2019, just based on the first two observing runs. What we've done since then is added in many of the black holes from the third observing run. Sorry, the colour scheme changes. The very first detection is now shown in black, but the improved Hubble constant using the third observing run binary black holes is shown in blue. And it's kind of tempting to say we seem to be homing in on lower values of the Hubble constant, but really it's still too soon to say. But it is giving us encouragement that as the number of sources steadily increases, we'll be able to refine our Hubble constant estimate more and more, and hopefully say something about this annoying Hubble tension that is a real puzzle for cosmology right now. So one way to represent that in terms of the last 20 or 25 years of observing is that back around the turn of the century, we didn't really know the Hubble constant well enough to realise that we even had a Hubble tension, because the error bars, the uncertainties, were still quite big, about 10%. But then in the years that followed, essentially two different sets of values emerged which didn't agree with each other. There was the methods using nearby data that give a slightly higher value, that's shown in blue, and then the methods using more distant sources that gave a lower value, shown in red. Now, our initial binary neutron star measurement really, again, was far too uncertain to really tell us whether the blue or the red was correct, or maybe another value in between. But what we would like is to be able to do exactly that. And our most recent results, published result with the third catalogue, is shown here. Again, the error bar shrunk a bit, but it's still, disappointingly large. But we reckon with something like about 15 binary neutron star mergers or a few hundred binary black hole mergers, we would be able to get much better precision. Will the value turn out to be about 70 or slightly below or slightly above? Well, time will tell. So watch this space. Hopefully that's going to be part of our upcoming results that we'll be publishing in the coming years. So what exactly will happen to enable all of that? Well, the analysis of our fourth observing run will be a big part. So in fact, this is more updated than I could have given you in February, because by now, our fourth observing run has increased the event rate. We've even had a very small contribution from CAGRA at the start of the fourth observing run, although they're still busy improving the detector for later. But you can see that there's been a rise in the rate at which we're detecting events, and we're now up to a total of 260. So that's 90 combined from the first three observing runs, which are all confirmed, and the others are candidates. We're still analysing them, but we're going to be publishing confirmations of many, many, many of these events very soon, in the next few months is the hope. And in fact, one we have published already. We published this last year. It's an event that happened on the 29th of May 2023, and it's another example of a merger of a black hole and a neutron star. We're pretty confident of that because we're able to estimate the masses quite precisely. But what's intriguing about this one is that the black hole is a kind of lower mass black hole than what we have seen before or what we've inferred from electromagnetic observations. So that black hole puts it in what astronomers have referred to as the mass gap, or sometimes the lower mass gap. And many astronomers don't really think it is a gap per se, it's just that we hadn't seen any black holes in that mass range. Well, now we have started to, and that's interesting in terms of what it might tell us about theories of how black holes form. So there's a lot still to learn about the fourth observing run, but this is the one event that we have so far, definitively said, yep, we did detect something. It's another merger of a neutron star and a black hole where basically we think the neutron star got swallowed in one gulp by the black hole, as you're about to see in the computer simulation. So watch this space for lots more about our fourth observing run. The fifth observing run, well, that will take us through towards the end of the century. Oops, sorry, too many slides. We'll have another gap from mid-25 through to early 27. And then our fifth observing run will have greater sensitivity again. So these numbers here are just an indication of how far out into the universe we could see a typical binary neutron star merger. We can see the binary black holes much further than that. So the number of events we're likely to be seeing should be taking us into the thousands by then. And we very much hope that that will unlock a lot of interesting new science. So in my final couple of minutes, let me just give you a sense of what's coming even further down the line. There are plans already building towards detectors in the 2030s, next decade, middle of the 2030s. And those are referred to as third generation detectors. And what they'll hopefully do is probe much deeper into the universe and also in a sense deeper into the past to a point when, well, kind of basically there weren't many galaxies, and we're seeing the very first galaxies and the very first generations of black hole mergers. So on the ground, there's plans afoot to build a European detector called the Einstein telescope, much bigger and more sensitive than LIGO. And there are a few possible sites, and we hope that a decision will be reached on where the Einstein telescope would be located within the next year. And to just try and again give you a sense of scale here, the kind of limit in terms of redshift or look back time, the look back times are in the bottom part, the redshifts. Oh, actually, I haven't shown redshifts in this one. Apologies. These are all just done in terms of look back time to make it a bit easier. So we can see back a few billion years right now with advanced LIGO. And as advanced LIGO gets more sensitive, we'll be able to see perhaps as far as 10 billion years back or more. But looking ahead to the Einstein telescope and then the American one, the Cosmic Explorer, just an artist's impression shown down here, then that really will push us out towards the first billion years or so after the Big Bang, when the very first galaxies were forming. And I would be remiss if I didn't just at least say a few words about an even more exotic mission than the Einstein telescope, which is planned for the middle of the 2030s, which is the LISA spaceborne detector. LISA stands for Laser Interferometer Space Antenna, and it's proposed to be launched around about 2037 or so, and it will be sensitive to even lower frequency gravitational waves than the Einstein telescope and LIGO and Virgo, and that will open up another part of the gravitational wave spectrum, analogous to how the electromagnetic spectrum was opened up by detectors in the 20th century. So LISA was officially adopted by the European Space Agency in January of this year. So that's why I think it's worth a mention for sure. This is a big step forward. And there's significant input from NASA as well, but it's an ESA-led mission. And a lot of the instrument work is being done at the UK Astronomical Technology Centre in Edinburgh, and building on the earlier work that was done in Glasgow, in fact, to build the optical bench for the LISA Pathfinder mission, which was a kind of technology demonstrator for LISA. So LISA will orbit the Sun in an orbit that will be trailing behind the Earth. The three satellites will be in a triangular configuration. And its principal target will be supermassive black hole mergers. And we expect that LISA will be able to see these very far out into the universe. And the kind of thing that we'll look to do with LISA will be to use those supermassive black hole mergers to measure the expansion rate of the universe, not just now, but how it's evolved over the history of the universe. And that might give us insight into possibly how dark matter and dark energy may have evolved over those 13 billion years. But really crucial to make LISA work will be, again, to find ways of obtaining redshifts of the sources as well as distances. We get the distances from the gravitational wave data, but the redshift we would principally look to EM to do that. And it will be instruments like the ELT, the Extremely Large Telescope, that you were saying you're going to get a talk on that in the coming weeks. And then perhaps also using the SKA radio telescope. Now, black holes, when they merge, probably don't give off an EM signature, but supermassive black holes are doing all of this within the accretion disk of an active galaxy. So we think there is a good possibility that there'll be an EM counterpart of the event that produces the black hole merger, even if it's not coming directly from the black hole merger itself, because it's kind of stirring up the gas in the accretion disk. So there's a lot of really interesting astrophysics going on there. And, if that does give us some insight into the nature of dark matter and dark energy, that would be amazing. Maybe we'll have made progress on that before 2037. But again, it's proving to be a real head scratcher exactly what the universe is made of. So if gravitational waves can do something to inform those questions, all the better. And I think for me, maybe even the more exciting possibility is something even more exotic, which is, well, if we can get distances from EM observations and we can get distances from gravitational wave observations, then in some theories, those distances will not agree with each other because gravity can propagate through extra dimensions, which the other fundamental forces of nature cannot. Now, I'm not saying that I think the universe does have those extra dimensions, but instead of it just being a purely theoretical question, if we can get to a point where we can actually experimentally and observationally test that, then that will be a really exciting development. So something I've worked on a bit in the last few years is to try to understand how well LISA, along with telescopes like ELT and SKA, might be able to answer questions about constraining the number of dimensions of space-time itself. So on that note, and again, forgive me if I've overrun a bit, I did take longer in the kind of prehistory than I'd meant to. I hope it's not been too rushed at the end, but I hope you've enjoyed my sort of exploration of the dawn, but more importantly, perhaps the exciting future of this new field of gravitational wave astronomy. And again, since I'm delighted to be speaking to you so close to Christmas, let me leave you with a happy Christmas message and Einstein with a Santa hat, which, seems appropriate to the occasion. But thank you very much again for the invitation, and I'll be delighted to have a chat now and answer some questions. Let me stop sharing.
Well, Professor Hendry, many thanks indeed. Mark promised us an interesting and entertaining talk, and it was that and more. And from a personal point of view, it was very accessible. So I really appreciate that on a Friday evening. So if we can all come off mute and thank Professor Hendry in the usual way. Okay, let's move on to questions. Did we have any questions in the meeting chat?
Yeah, there's one from Ian. Ian, are you there?
Yes, it's a slightly lateral question. You mentioned that a gravity wave has a potential of 1,000th of a diameter of a proton in perturbation. I'm just wondering if that would have any measurable influence on the rate of radioactive decay of isotopes.
None that I'm aware of, Ian. I'm afraid that's a bit outside my area of expertise. But again, because gravity is so weak, I don't think that gravitational perturbation to the interactions that are driven by the strong and weak nuclear forces would have any effect at all.
So the space-time effect wouldn't affect it either?
No. On the other hand, in the very early universe, round about a billionth of a second after the Big Bang, when nucleosynthesis was occurring, then the presence of gravitational waves back then could have been more important. This is the kind of thing which you'll maybe recall, I think it's a decade ago, crikey how time flies, there was a report of a discovery of those primordial gravitational waves from the BICEP 2 experiment at the South Pole. What they were looking for was not a direct detection, but the imprint of gravitational waves on the polarization of the cosmic background radiation. So from a kind of switching hats from a gravitational wave hat to more a sort of theoretical cosmology hat, we do think that gravitational waves could have had influential effects in the very early universe, because the different fundamental forces would have been more on an equal footing back then. And, ultimately, we need to come up with a theory of quantum gravity. But even, long after the kind of quantum gravity regime, which is more like 10 to the 30 minus 32 seconds after the Big Bang, you've still got in that few billionths of a second through to the first 3 minutes after the Big Bang, a lot of interesting stuff going on in terms of the formation of radioactive isotopes, and understanding how the presence of primordial gravitational waves could have influenced some of those parameters. That's work which, I didn't really do it justice. I showed this slide of the gravitational wave spectrum and immediately homed in on LISA. But along at the left-hand end of that diagram was the cosmic background radiation. And, although BICEP 2 turned out to be a false alarm, we do want to study the CMBR and try and work out what gravitational waves might have been present in the very early universe, and perhaps explore some of these more exotic effects on how things like nucleosynthesis would have unfolded. So, your question's certainly relevant to that era, but not the kind of events that we're seeing now in the relatively recent past.
I was hoping I could make a backyard observatory. Gravity wave.
I think you'd probably have to go to the South Pole to do it, so that might be a bit more challenging.
Thank you.
The whole BICEP 2 story was a fascinating one for us, because it unfolded just really a year before our first detection, and it maybe kind of made us even more cautious about claiming a detection, because we'd seen how BICEP 2, the paper actually didn't overclaim, but a lot of the media around it was quite sensational, and we wanted to, avoid that happening if we possibly could. But at the same time, of course, everybody loves black holes. So we woke up on February 12th to discover 900 newspaper front pages. Fortunately, I think we got it about right and not overclaiming and so on. And we certainly would have been mighty embarrassed if we'd had to retract our detection. So again, we were extremely careful.
Okay. Thank you.
I think we have a question from Nigel. Do we, Nigel?
Yes, thank you very much. Thanks very much, Martin, for a fascinating talk. I just wondered that whether you expected the rate of detections of different events to continue climbing in the way that it has since the end of the second observing run and the start of the third, as instruments become more sensitive.
We do indeed, but I think it's only fair that I note that it isn't going to be all sweetness and light, because actually by the time the Einstein telescope comes along, again, it's not fully approved yet, but we've made good progress in like through EU funding and so on. Let's be optimistic and see that is going to be operational towards the end of the 2030s. It is reasonable then to expect that we'll be seeing of order 1 million binary black hole events every year, but there's only 31 million seconds in a year, and a lot of those events will last many seconds, even minutes. So basically, one of the things that we're trying to get our head around right now is, will we still be able to do as good a job in characterizing all these events when they actually overlap with each other? So although the more and more events is good, it's really causing us to scratch our heads a bit in terms of how we will do the data analysis when there's just so many. Now, LISA's a bit different. The number of supermassive black hole binaries that LISA will see is much more manageable. It's like, maybe a few hundred. So the chances are they won't overlap at all. But the events will last for a long time, more like weeks to even months. But because they'll be in different parts of the sky, and LISA, the three satellites are 2.5 million kilometers apart, so we'll be able to pinpoint their position much, much more precisely, and we will therefore be able to kind of disentangle them. The circumstance for LISA that is more problematic is white dwarf binaries in our galaxy. They are much lower frequency gravitational waves, and we won't necessarily see them merging. We'll just see them giving off a kind of low hum of space-time distortion as they're just orbiting each other, and maybe, you know, still quite close together, but with orbits perhaps a few hours in duration in period. Now that's all great, you know, fascinating to have the opportunity to observe that. But again, we'll be seeing maybe, you know, hundreds of thousands, if not millions of those events, and they will all overlap. So that'll be more like a kind of background chorus of white dwarf binaries. So actually a lot of the data analysis challenges there are really quite fascinating, just trying to work out how we might separate those events. And as you might not be surprised to discover, we're sort of looking at how we might use things like, you know, generative AI, well, machine learning methods, not necessarily generative AI, but AI methods to help with the separation of all of these overlapping signals. So, you know, rather long answer. Short answer is yes, definitely, but it's not going to be as straightforward as you might hope to disentangle the information about all of those extra sources.
Thank you very much.
I think we have another question from Jim Barron. Are you there, Jim?
Yes. Thank you very much for the talk, Martin. I was wondering, in terms of you measuring the distance to the gravitational wave effect, is that along the, I'll put the question simply, but in inverted commas, because is that along the lines of applying the inverse square law against what you estimate the power at the source to be versus the measured power? But are there things along the path that could attenuate the signal in other ways?
No, but brilliant question. I'm so glad you asked that, because again, these are all details that I didn't want to kind of clog up the talk by getting too bogged down in them, but I'm glad you've asked. So again, the short answer is yes, more or less, but the devil's in the detail here. Firstly, what we're actually detecting is the amplitude of the gravitational wave signal that reaches us, not the, well, the amplitude squared in the case of an electromagnetic wave. So basically, the dependence with distance falls off as 1 over r, not as 1 over r squared. Now that's actually a good thing, because it means in principle we can see the gravitational waves further away. Like if we, you know, if we improve our sensitivity, you know, we're actually gaining linearly in distance rather than the square root of distance. So that's all good. But yeah, the other point you make about the attenuation, well, short answer there is not really, in the sense that, you know, you can lose a lot of the light power that reaches us by things like scattering off dust and so on. The equivalent for gravitational waves would have to be like scattering off another black hole, you know? The gravitational waves will just bowl on through the universe as if nothing's there, unless they encounter a very dense region of space-time where the space-time curvature is appreciably changed. Now, I just said a moment ago that with, say, the Einstein telescope, we're expecting to observe hundreds of thousands, maybe even millions of events. So actually, with that many events, there's a very good chance that a distant gravitational wave source actually will encounter a disturbance along the path that would distort the waveform. This will be what we call gravitational lensing. So whereas you get gravitational lensing of light, and that's just sort of routinely observed now, we haven't seen that for gravitational waves yet, but we fully expect that we should. And in fact, there's some quite subtle differences where you get like wave optics effects, whereas if you know the terminology, geometric optics is fine for light. In most of the situations we encounter, you don't have to account for diffraction and other kind of messy maths that comes in. But with the gravitational wave ones, if we see lensing, it's possible we'll also see diffraction effects. Now, that's both a challenge and an opportunity, because actually that could give us really good insight into, like, you know, one of the ideas of what dark matter might be, I'm not saying I necessarily subscribe to this, but in fact, former faculty member in Edinburgh, Mike Hawkins, was a great proponent of this for a long time, which was that dark matter was primordial black holes. Now, if it really is primordial black holes and they lens the black hole gravitational wave signal from further away, then that will have a very distinctive diffraction pattern. You'll see wave optics effects that you wouldn't get if the dark matter is more smoothly distributed, like it's, some elementary particle, like most people think dark matter probably is. So that would just give us another way to test what the properties of dark matter are. Totally different using sort of diffractive versus geometric optics effects. So your question is very timely, actually, because I co-organised a workshop in Manchester back in March, trying to get the gravitational lensing community together, the people that work on gravitational wave lensing and the people that work on EM lensing, to try and get our ducks in a row as to what kind of things we might look for in the coming years, and that could really kind of push on towards, well, exactly what your question says. Is there anything causing disturbance of the gravitational wave along the way? And if so, how would it look different from the disturbance of an electromagnetic wave? So sorry for the long answer, but again, ask me back in a couple of years and I might well have some interesting answers to that. We haven't seen anything yet, but you can't have one prediction of Einstein without the other. So, somewhere down the line, we're going to see gravitational wave lensing, and it will be very much like what you're asking about.
Sounds fascinating. Thanks very much.
That's all the questions.
Can I just ask a follow-up to Jim's question there?
Sure.
Mike Christie. If you do see that, is that not going to make the sort of calibration, the inverse problem of the model, much more complicated to deal with? Because my understanding is that you're doing numerical solution of the field equations to get the characteristic chirp, and then you're calibrating those to get the mass and the distance. But if you've then got to account for diffraction effects on the way here, it seems to be orders of magnitude harder. Have you had any thoughts about that?
With lots of thoughts. We've published lots of papers on it too. I have a grad student who's working on exactly this. He's from Korea, and he's working with colleagues in Korea on specifically what extra information you could get about an individual gravitational wave source if you knew it was lensed and you incorporate into the lensing model, estimating the additional parameters due to the lensing. So that's like the best you could do. But the worst you could do is if you didn't actually know it was lensed, it would sort of bias your parameters. So again, we're trying to get a handle on how big an effect that is. Sometimes you would overestimate the distance. Actually, sometimes you would underestimate it as well. Because what you can have is a source that's in a line of sight, which is sort of like emptier than the average, and that can cause actually a kind of divergence of the gravitational waves. So these effects have been looked at a great deal on the EM side. We're slowly catching up on the gravitational wave side, and I see we're very much on the case. And in fact, that's principally what that meeting in Manchester was about. So there's going to be papers from that coming on. Actually, we're supposed to be submitting one to the archive first week in January, so I'll be happy to send a link to Nigel and the others. Feel free to have a read. It's setting out a kind of white paper of all the types of science you could do if you had a lensed event that was seen in both gravity and in light. And it's sort of recognizing that in some cases, if you're not careful, it could really mess things up. But if you do model it carefully enough and take all of those effects into account, then you could actually wind up with more information than you would otherwise have.
Sounds really interesting. Thanks.
Okay, thanks everyone. I think that concludes all the questions from the Zoom chat. Will, do we have any questions from the YouTube audience?
No questions from YouTube, but incredibly wild talk. Amazing. Thank you.
As I said, sorry I couldn't be there in person back earlier this year, but in fact, in February, we hadn't had that workshop in Manchester. That took place in mid-March, so maybe it's an ill wind because by delaying, I'm able to, see a little bit more in answer to that question from Mike there. But yeah, it's very much a case of watch this space, or maybe it should be watch this space time. A lot has happened in the last decade, but there's much more to come. I think it's a sort of bright future. So I hope to be able to share that with you again on another occasion.
We'll look forward to it. If we could say thanks again to Professor Martin Hendry for this evening's talk.
Excellent.
Everybody.
Thank you.
Merry
Great
Christmas.
talk, yeah.
Take care.
Excellent.
Bye-bye.
Thanks all. Merry Christmas to one and all, and we'll bring this evening to a close. I hope you have a wonderful time over the festive season, and we look forward to seeing you all in 2025. Good night.
Cheers. Good night.
Good night all.
Bye-bye.
Cheers.